So we are very, very happy to have Josh Shalha from Columbia, who will tell us about classical Walsh-Hadamard Transform.
Thanks. Yeah. Hi, everybody. Yeah. So today I want to tell you about the Walsh-Hadamard Transform. This is what I'm going to tell you is like, I guess, a accumulation of a few recent papers, but most of it is joint work with Yunfeng, Guan, and Ashwin, Padaki, and Kevin Rao, who are Yunfeng and Kevin are master students, and Ashwin's an undergrad. So it's lots of students getting into just starting to do research. Okay, so what is the Walsh-Hadamard transform? I guess so. The Walsh-Hadamard transform, I guess, is my favorite family of matrices, and maybe my biggest goal for the talk is that by the end, it will hopefully also be your favorite family of matrices. So it's defined recursively like this. So when n is a power of 2, the n by n Walsh-Hadamard transform is a matrix of -1s and 1s, where the first one is this 1 minus 1 1 1 matrix, and then in general the nth one is 4 copies of the n over 2th one, where you negate the top right one. So indeed, this picture from my title slide is the first few of them, and you can see each one is like 4 copies of the previous one, but you negate the top right copy of it. And the problem I want to talk to you about is the algorithmic problem of computing the linear transform defined by this matrix. So in other words, the problem where you're given as input a vector of length n, and you want to output the Hadamard transform times the vector. So you can think, actually everything I'm going to say in this talk will work over any field, but maybe it's easiest to think of working over the reals or the complex numbers. One thing is, usually when you're designing algorithms and your inputs are real numbers and your outputs are real numbers, there are lots of details like about those numbers that sort of determine what the running time is. Like maybe they're really big, or you need to manipulate them with lots of precision, and like these can impact the running time at the end. But I want to abstract away all those details. So I'm gonna focus today on just counting the arithmetic operations that an algorithm for doing this uses, and then you could multiply that by how long it actually takes to do operations with whatever numbers you're working with. So there's sort of a straightforward algorithm for this, which is just to multiply any n by n matrix times a length n vector. You can do with order n squared operations by just following the definition. And we'll see in a second that the Walsh-Hadamard transform has much faster algorithms than that. Okay, so why do we care about this problem? So these matrices really come up in a lot of different situations. This is it's like sort of a discrete, some kind of version of the Fourier transform, which you've probably seen before. It has lots of applications similar to the discrete Fourier transform in signal processing and data encryption and compression. It's like a basic gate in quantum computation, if you've seen that before. It somehow comes up a lot in algorithms and complexity. Let me give you sort of 2 examples. So one is that if you're given as input the coefficients of a polynomial, a multilinear polynomial in n variables, then the Walsh-Hadamard transform times the vector of that coefficients evaluates that polynomial on all points in -1, 1 to the n. So if you've seen before, like Fourier analysis of the Boolean hypercube, this is the Fourier transform you're talking about when you're doing that actually evaluates the polynomial on all the points. And for another example, that's actually a newer one that I'll tell you more about later in the talk. Actually, the Walsh-Hadamard transform can be used as a subroutine in the best FFT or DFT algorithms. So if you haven't seen this, but you have seen the FFT, this can also be used to speed up the FFT. So it's useful in that situation also. Okay, so how do we compute it? There's a nice, very simple folklore algorithm called the fast Walsh-Hadamard transform. Here's how it works. It's just a nice recursive algorithm based on this recursive definition. So when you're given as input a vector of length n, and you want to compute the matrix times the vector, you first split the vector into 2 parts of length n over 2, and you recursively compute the n over 2 size Hadamard transform of each of them, and then you combine them together in the way defined by the recursion. So you output the top half of what you output is their sum, and the bottom half of what you output is their difference. And this computes it, and you get a nice recursion that the time to do of size n is you do 2 of size n over 2, and then order n operations to add and subtract these two vectors of length n. And it solves to n order n log n. And in fact, if you care about the constants, it's exactly n log n. Like this is 1 times n operations, and the leading constant here is really 1. Okay, so it's very simple. Let me show you this algorithm in a slightly different way, which is going to be useful for how we're going to generalize it. So I'm going to want to think of the fast Walsh-Hadamard transform as a way to factor the Walsh-Hadamard matrix as a product of a few really sparse matrices. Okay, so yeah, so that's what I just said. So here's the idea. Here's our Walsh-Hadamard transform. It's defined recursively like this. And one step of the recursion I just showed you, you can see is very similar to factoring the matrix like this. So you first do 2 different Hadamard transforms of size n over 2, and then you combine them with these identity matrices, where at the top you add the 2 results, and at the bottom you subtract the 2 results. But you can keep doing this. Like if we do another layer of our recursion, we can replace each of these hn over 2s with, like, first you do hn over 4s, and then you do add and subtract the results on the 2 sides, and so on. So you could keep doing this, replace the hn over 4s with hn over 8s, and so on. And what you'd get at the end is you'd write it as a product of log n different matrices, and each of these is sparse. You can check, like, this matrix, each of these identities has n over 2 non-zero entries, so this has 2n non-zero entries. You can check this one also has 2n non-zero entries, and so on. So we've written it as the product of log n matrices with order n non-zero entries each. And yes, sorry, yeah, there shouldn't be a minus there. Yeah, you're absolutely right. Yeah, sorry about that. Okay, so these factorizations of an important matrix as a product of a bunch of sparse matrices are pretty well studied, and they're usually called a linear circuit for computing the matrix. So you say if you have some matrix M and you factor as the product of d sparse matrices, we call it a linear circuit where the depth is d, the number of those matrices, and the size is the sum of the number of non-zero entries in each of the matrices. Okay, and then the idea is that if you want to multiply the matrix times a vector, you can do it in order of that size operations by first multiplying AD times the vector, then multiplying AD minus 1 times that, and so on. And you can multiply a matrix times a vector in number of operations proportional to the number of non-zero entries. So that's why that's the way I measure the size. So using this fast Walsh-Hadamard transform idea, I just showed you that it has a depth log n circuit of size n log n. There's log n different matrices of O of n non-zero entries each. It also, and I'll show you more details about this later, has a depth 2 circuit of size n to the 1.5. So sometimes you want to work with smaller depth circuits, for example, to make parallel algorithms. So if you want a depth 2 circuit, you can get one of size n to the 1.5 in a very similar way. Okay, so that's the background about the fast Walsh-Hadamard transform. And let me now tell you the 2 results I'm going to show you today, which are both ways to improve that fast Walsh-Hadamard transform that I just showed you. So this is like a sort of a basic folklore algorithm that's been around for a long time and is really used in these different applications I told you about, but I'm going to show you how to improve both of those circuits I just mentioned. Okay, so here's the first result. I'm going to show you how to get a depth 2 circuit of size n to the 1.45. So the fast Walsh-Hadamard transform gives size n to the 1.5, and I'm going to improve it to n to the 1.45. And this is based on joint work with Guan and Padaki that was in Soda earlier this year. Okay, so this is an improvement. Let me mention one particular reason I think this is interesting. So this actually overcomes a barrier to trying to design better algorithms for the Walsh-Hadamard transform. So there's a result by Pudlak from 2000, who showed that if you restrict yourself to working with a special kind of circuit called bounded coefficient circuit that I'll define in a second, it's actually impossible to beat size n to the 1.5. So by bounded coefficient circuit, what I mean is that when we have this factorization of the matrix into a product of two sparse matrices, all the entries of those matrices should be where we're working over the complex numbers, and they should be complex numbers of at most constant magnitude. So they're the coefficients and they're bounded. And if you like look at how the fast Walsh-Hadamard transform works, really all the coefficients are just ones and minus ones. So they really are constant, a constant bounded coefficient circuit. So there's actually a lot of work starting with Morgenstern in the 70s who showed that for lots of matrices like the Hadamard transform and the Fourier transform and so on, you really can't improve on sort of the algorithms we know using just bounded coefficient circuits. And I think this is at least the first result that I know of, which is sort of non-trivially getting an upper bound that circumvents one of these bounded coefficient lower bounds. So we're gonna actually beat the lower bound using unbounded coefficient circuits. Yeah.
A quick question. So you're mentioning in the beginning that your model here, you're counting the number of operations. So if you're not, you're going to eventually then use entries that are not constant size, so they might be like super constant.
Yep.
But you're still assuming that it still counts like one operation.
Yeah. It turns out they won't be very big. Like they'll be log n bit numbers that we're going to use. So even if you did sort of count the contribution from that, it's less significant than the end of the 0.05 improvement. But yeah, that's a great question. Okay, so that's the first result I'll tell you about. And then the second result is an improvement for the case where we don't care about the depth and we really want to count the number of operations. So I'm going to show you a new algorithm that uses 0.96 times n log n operations, which improves the constant factor from 1 to 0.96 of the fast Walsh-Hadamard transform. Yeah, I think pretty much everyone believes that you can't beat like order n log n, but I mean, there's barriers like, for example, about bounded coefficient circuits, but I don't know of any like, we certainly don't have any unconditional lower bounds saying you can't beat n. Yeah, there's like, yeah, not really, not that I know of. But this is, I mean, as far as I know, this is the first improvement at all on just the standard folklore fast Walsh-Hadamard transform. I'm not sure. I think if you I'm honestly not that sure what people believe. Like, I think before people didn't believe you could beat n to the 1.5 for depth 2, and then we beat it only pretty recently. I actually haven't asked that many people what they believe anymore. Oh, I think it's hard. Yeah, like these bounds from like the ways you can prove lower bounds for like integer multiplication using sorting networks. I think you can do the same kind of thing here also. Yeah. Yeah, I honestly don't know what the answer should be. Okay, so let me briefly mention the application I promised you before to the speeding up the fast Fourier transform. Okay, so here's my one slide about FFT algorithms, and I'm not even going to define what FFT is. I'm sort of assuming you kind of know what it is, and if you don't, this is the only slide that's going to be about it, so don't worry too much. Okay, so here there's a similar kind of question of what's the smallest constant a, so that you can do the DFT with a times n log n operations. And this problem, there have actually been a number of improvements to. Like, so there's the famous Cooley-Tukey algorithm, gets a leading constant of 5. And then a few years later, they found you can do something called a split radix trick to get it down from 5 to 4. And then all the way later in 2007, Van Buskirk showed you can improve it even more to 3.777. This is actually, I think this improvement's really funny because Van Buskirk didn't like write a paper about this or something. He just posted code online on Usenix and said, hey, everyone, check out this cool new FFT code I have. And it took people actually 3 years after he posted it to figure out what the leading constant of his algorithm was. But people really use this, like if you look at the most popular software packages for doing the FFT, like this modified split radix algorithm is actually implemented and used in them. And then a bit more recently, Sergeyev showed that you can sort of take the ideas of this modified split radix to the extreme and improve it a little bit more. I think this last one here is not really a practical algorithm, but the other ones actually are used. Okay, so one thing Kevin Rao and I proved recently is a kind of reduction from the DFT to the Walsh-Hadamard transform. So what we show is that if the Walsh-Hadamard transform can be computed with leading constant C, then the DFT can be computed with leading constant, this expression, 2/3 C plus 28/9. Okay, and so in particular, if you plugged in C equals 1, like the folklore algorithm, you'd recover this modified split radix leading constant. But if you plug in our new improved 0.96 for C, you get a slightly improved 3.75 leading constant for the fast Fourier transform. Yeah, I don't, I know these are all like fall in my favorite kind of result of getting very small improvements to constants, but I think the idea of, like, as far as I know, there weren't any connections showing like an improvement to one of the FFT or the Walsh-Hadamard transform would improve the other. So I'm kind of excited that maybe more substantial improvements along these lines might be possible later. Oh yeah, specifically like cyclic group over complex numbers. Yeah, power of 2. Yeah, yes, that's right. Yeah, exactly. Yeah, it breaks down totally when it's not power of 2. Okay, so let me now, for the rest of my talk, actually tell you about how we get these better Hadamard transform algorithms. And I'm going to start with the depth 2 circuit, and then the second one will sort of build on these ideas. So I'm going to show you how to beat size n to the 1.5 with a depth 2 circuit for the Walsh-Hadamard transform. So in the paper, we get n to the 1.45. In this talk, I'm just going to show you how to beat 1.5 a little bit. I'll get to like 1.49 to go from there to there. It's the same high level idea and a lot more details and tricks and things like that. Okay, so first I want to introduce one piece of notation, which is going to be very helpful to us, which is the Kronecker product. So here's how it's defined. So if you have two matrices, an A by B matrix X and a C by D matrix Y, their Kronecker product is an AC by BD matrix. So you have one row for each pair of rows and one column for each pair of columns. And it's defined like this. So for each pair of an ij entry from X and an I prime J prime entry from Y, there's an entry whose row corresponds to the pair of rows and column corresponds to the pair of columns, whose value is the product of those two values. So just as an example, here are two different 2 by 2 matrices. And their Kronecker product is a 4 by 4 matrix. And you can see it looks like 4 different copies of this left matrix here, 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 and here. But then each one I rescaled by like the value in the second matrix. And for each pair of an entry in the first and an entry in the second, there's an entry in their Kronecker product. Okay, yeah, if you've seen like tensor product before, this is the same thing, except like usually the tensor product of two matrices would be a 4-dimensional tensor. Here I'm flattening it back to be a matrix instead. Okay, why do I want to use the Kronecker product? So it has two key properties which we're going to take advantage of. The first one is that the Kronecker product is really the correct way to define the Walsh-Hadamard transform. So like if you look at the recursive definition we had before and the definition of Kronecker product right now, you can see the n by n Hadamard transform is exactly the log base 2 of nth Kronecker power of the 1 minus 1, 1, 1 matrix, like the Kronecker product of log n copies of it. Okay, so it's useful for the Hadamard matrix. And the second one is that it has something called the mixed product property, which the way I'm going to use it is as follows. It says that if M is the product of A times B, then the mth Kronecker power of M is the mth Kronecker power of A times the mth Kronecker power of B. Okay, this is not like I don't want to say it's not a deep fact. Like the way you prove this is you just write down the definitions and notice that they're the same as each other. But it's going to be very useful to us. The idea is that, so now in order to construct a depth 2 circuit for all like arbitrarily large Hadamard transforms, it suffices to make a depth 2 circuit for any one particular Hadamard transform and then take Kronecker powers of it. So if we had a circuit for HK for any fixed K, we can take the Kronecker power to get Hn for any n, and our circuit would be just Kronecker powers of the 2 matrices we used for our fixed one. So I'll show you an example in a second, and I'll just note, because we're going to use this a bit later, there's even like a more general fact that the Kronecker product of the regular products of any 2 matrices is equal to the regular product of the Kronecker products, assuming like all the dimensions work out appropriately. Okay, so let me show you more concretely how we'll use this. I'm going to show you how what the depth 2 version of the fast Walsh-Hadamard transform is. So here's the idea. Let's first gonna do just one step of that fast Walsh-Hadamard transform, like matrix factorization that I told you about before, to get just a depth 2 circuit for the 4x4 Hadamard transform. Okay, so here it is, a 4x4 Hadamard transform. It's 4 copies of the 2x2, and we do this one step we talked about before, right? 4 copies of identity and 2 copies of H2. Okay, so this is a depth 2 circuit for the Hadamard transform. And now to get a circuit for any Hadamard transform, I'm just going to take Kronecker powers of this. So for any n, let's say n's a power of 4, okay, to make it work out. The 4x4 Hadamard transform is the log base 4 of n Kronecker power of H4. And so that means we can write it as the product of the first matrix to the log base 4 of n times the second matrix to the log base 4 of n. So this is a depth 2 circuit. And now we have to count how many non-zero entries are in each of these matrices. But conveniently, because in the Kronecker product, like each entry in the result is the product of 2 entries from the input matrices. So the number of non-zero entries in a Kronecker power is just the power of the number of non-zero entries in the first matrix. In our case, we can see this matrix has 8 non-zero entries, and this matrix has 8 non-zero entries. So this gives a circuit where both of the matrices, the number of non-zero entries is 8 to the power of log base 4 of n, which is n to the power of 1.5. So just taking this fixed construction for the 4x4 matrix and then Kronecker powering both sides gives you size n to the 1.5 depth 2 matrix, depth 2 circuit. Okay. Okay, any questions about that? Great. So let me tell you now how we're going to improve on this. Here's the plan. So first, like sort of as I've been suggesting, what we're going to do is just construct an improved depth 2 circuit for one particular Hadamard matrix. It'll turn out we're going to do it for the 64x64 Hadamard matrix. And then you take that and you Kronecker power it in the exact same way, and it gives an improved circuit for all Hadamard matrices. Okay, that's the plan. That's what we're going to do. How would you go about getting an improved depth 2 circuit for the 64x64 Hadamard transform? Maybe your first idea, and this was my first idea, is to just do some kind of computer brute force search thing. The problem, I mean, I'm sure some of you are better at computer programming than I am, but somehow 64x64 is already a big enough matrix that there are like too many options to brute force over, and it does not seem to work very well. So I'm going to use a more principled approach to find this, using something called matrix rigidity as maybe more the intuition than like directly using it. So let me tell you what matrix rigidity is, and then I'll show you how we're going to use it. So matrix rigidity, we say that a matrix is rigid if it's far away from any low rank matrix in Hamming distance. So not only is it high rank, but it's far from any low rank matrix. So more specifically, this notation, we write the rigidity for the matrix M of rank R is the minimum number of entries in the matrix M that you have to change to make its rank be at most R. So let me give you some examples. So if we're working with the n by n identity matrix, then for any rank R, you can see its rigidity for rank R is n minus r. So if you change n minus r of the ones to zeros, you'll get a rank r matrix. And it's not hard to see that that's tight, because whenever you change one entry of the matrix, you can change the rank by at most one. So you really have to change n minus r entries to get from a rank n matrix to a rank r matrix. Okay, that's probably the simplest example. In contrast, it's known that a random n by n matrix, let's say over F2, but like in pretty much any situation, is very rigid with high probability. If you have a random matrix and with high probability, to get to, let's say, any sublinear rank, you need to change a constant fraction of all the entries in the matrix. Okay, so like the identity matrix is very not rigid. A random matrix is very rigid. Rigidity was introduced in the 70s by Leslie Valiant. And he actually introduced it as a way to try to prove lower bounds for these linear circuits that we've been talking about. So what he showed is that if you have any matrix and it's computable by a really small circuit, a linear size log depth circuit, then that means that matrix is not too rigid. For some parameters, you can change just n to the 1 plus epsilon entries to make its rank really sublinear. So he showed any matrix that's computed by a linear size log depth circuit is not too rigid. And this is like, he presented this as a way to try to prove circuit lower bounds. So like if we wanted to prove that the Walsh-Hadamard transform can't be computed by like a linear size log depth circuit, like we were just asking about before, one way you could do it is to prove it's rigid. It does not have this rigidity upper bound. Yeah, I'll show you in a second. We sort of have given up on this approach. But what I'm going to tell you about can be kind of seen as a converse of what Valiant was talking about. He used a small circuit to give a rigidity upper bound. We're going to use rigidity upper bounds to give small circuits instead. It's not exactly a converse, but it's a conceptual converse at least. So what do we know about the Walsh-Hadamard transform's rigidity? Well, so a few years ago, Ryan Williams and I showed that actually the Walsh-Hadamard transform is not rigid enough to prove lower bounds using Valiant's approach. So we showed that the detail's not super important, but for any epsilon, you can change n to the 1 plus epsilon entries and make its rank go all the way down to n to the 1 minus epsilon squared. Whereas you would have needed there to be an epsilon so that you can't get below rank like n over log n to be able to use Valiant's approach to prove a circuit lower bound. So we know it's not rigid enough to prove lower bounds in that way. And one nice thing is that if you think about it a little bit, rigidity upper bounds really naturally give depth 2 circuit upper bounds. So for any matrix M and rank R, it has a depth 2 circuit of size just depending on the rigidity. The idea is just if you can write the matrix as the sum of a low rank matrix, U times V, plus a sparse matrix, then like the low rank matrix naturally gives you a depth 2 circuit of size, I guess 2 times R times N, and the sparse matrix naturally gives you a depth 1 circuit of where size is the number of non-zero entries in it, like the rigidity of the matrix. So generally speaking, you can use this and then try to balance R to get the smallest circuit you can. Like as R gets bigger, this first term gets bigger and the second one gets smaller, because like as the target rank gets bigger, you don't have to change as many entries to get to it. And you can do this using our rigidity upper bound, and you show that there's really a delta bigger than 0 such that the Hadamard transform has a depth 2 circuit of size n to the 2 minus delta. And this is non-trivial in that like almost all matrices really require size roughly n squared. So we're really beating that. But on the other hand, it's actually kind of disappointing, I think, because I just showed you a circuit of size n to the 1.5. And using this sort of high-powered rigidity upper bound, I tried quite a bit and I have not figured out how to use it to actually beat n to the 1.5. So nonetheless, we're gonna sort of use this as motivation to beat n to the 1.5, but we're gonna use actually a way less complicated rigidity upper bound to do it. So let me show it to you. It's very simple. We're gonna study the rigidity of small Hadamard matrices for rank 1. Okay, so here's the main idea. Let me first show you how the 4x4 Hadamard matrix, its rank 1 rigidity is 4. So here's how we do it. Here's the 4x4 Hadamard matrix, and here's a rank 1 matrix that I claim first you can check it differs from it in only 4 entries. And you can check it really is rank 1 because each row after the first one is in the negation of the first row. Okay, so this has written this shows that it's at most 4. You can actually see this is tight, so it's exactly 4. Okay, maybe I won't get into it now. But you can show this is tight. You can't change 3 entries of the matrix to make its rank 1. Okay, but the intuition was kind of just in this Hadamard matrix, like all of the -1s are in the bottom right part. So we put all our -1s in the bottom right part to match it. Okay, and you can do the same thing with the 8x8 Hadamard matrix and find that you can change 22 of its entries to make it be like this all -1s in the bottom right part and -1 in the top left and 1s in the left, which is still a rank 1 matrix. Okay, this turns out is also tight and it's less easy to prove it, but you can prove it. You actually, yeah, I think you get 23 if you do that. You have to, it turns out one of them you improve, you will have to work a tiny bit harder than that, but not very much harder. Yeah. Okay, this is the rigidity upper bound we're going to use. In the whole paper, we actually use a slightly more complicated rigidity upper bound, but to get some improvement, we can just use this. Okay, so here's how we use it. Okay, so we're just, like I showed you before, we're going to convert that rigidity upper bound into a depth 2 circuit for H8. Okay, so we know we can write H8 as the sum of a sparse matrix S with 22 non-zero entries and a low rank matrix of rank 1, which is like the outer product of 2 vectors. So we can combine them together to make a depth 2 circuit. So we can write it as C times D, where C is S and then the vector U, and D is the identity matrix and then the vector V. So when you multiply them together, you get S times the identity plus U times V, which is exactly our rigidity bound and recovers the matrix H8. So there's our construction for H8, and now we just have to take Kronecker powers of it, right? So we can count the number of non-zero entries. In C is 30, and in D is 16. And so that means that in general, Hn has a depth 2 circuit of size, the bigger of the two, which is 30 to the log base 8 of n, which is unfortunately a bit worse than we were hoping for. But we're just going to do one quick step at the end to, like here, C has a lot more non-zero entries than D does. So we're going to do one balancing trick to make them have roughly the same number. So like in addition, because H8 is symmetric, or maybe if you permute the entries, then permute the rows, then it's symmetric. We could also write it basically as D transpose times C transpose. And so now we'll use that mixed product property I told you before, and we can write H64 as the Kronecker product of 2 copies of H8. And one of them, we write them as C times D, and the other one we write as D transpose times C transpose. So when you take the Kronecker product of them, we write H64 as C Kronecker product D transpose times D Kronecker product C transpose. Okay, this is our symmetrizing step. And now we really do, using this identity for H64, get a circuit for Hn whose size is the number of non-zeros in each of these, which is 30 times 16 to the power of log base 64 of n. And if you put that into your calculator, it will tell you it's n to the power of 1.49. So that's really the whole idea. But the intuition is we should try to use rigidity upper bounds to construct these circuits. And we honestly just tried a bunch of things until we found one that worked. It ended up being quite simple. Okay. Any questions about that? I'm going to move on to the second result now. Yeah.
Second question, n to the 1 point stuff for 5 dimensions. Is it also with n equals 64, or did you like house that?
I think it ends up being using 256, something like that. Yeah. It uses a decomposition of H16 instead of H8 and uses it in a slightly different way. Yeah.
So is 1.45 the limit of your current ideas, or just as much cases as you had?
It's the limit of, I think we have proved that if you just use a rank 1 rigidity upper bound together with like this kind of idea and maybe some other tricks we found, that's the best that you can get. I suspect there's other ways to improve on it more. But yeah, it's not like, you know, you could look at 16 instead of 8 and beat it more, but yeah, I suspect there's more improvements that are possible for sure. Yeah.
Sorry, I probably should be able to figure out but where is the size of why are the entities growing?
Oh, so this, yeah, I sort of hit this, but so this matrix S, it's 22 non-zero entries are all 2s, like because they have to change from -1s to 1s. So when you take the Kronecker power of it, the entries are 2 to the power of something. Yeah, that's where it's coming from. So if we took Kronecker products of things with just 1s and -1s, we wouldn't get that. But because S has 2s in it, we get growing coefficients. Yeah. Oh.
They're literally just, so it's just 2 to the power.
Yeah, the biggest one is 2 to the power of log base 64 of n. Yeah.
Does that say, like, even if you were to be very pushy about the runtime of multiplying numbers, is that?
Yeah, like if you just want to do it with integers, you can do these things with bit shifts and they don't change the number of bits very much. Exactly. Yeah. I don't know how to do it in polynomial time. I can do it in like singly exponential, like exponential in n time instead of like exponential in n squared time, which I made use of to come up with these things. I don't know how to prove it's hard, though I suspect it probably is hard. Yeah. Yeah, there's some tricks you can use for rank 1 that break down even at rank 2 or 3 to simplify it a little bit. Okay, so let me move on to the next result. Actually, how much time do I have left? I lost track of when we started or when we're supposed to end. 20 minutes. Okay, perfect. That should be plenty of time. So let me show you the second result now with together with Kevin Rao. It was actually just accepted to the upcoming stock a few days ago. Okay, so we're gonna improve again. I'm not gonna care about restricting our depth somehow, and I wanna improve the number of operations from n log n to 0.96 times n log n. Okay, so the high level idea is going to be very similar to what we just talked about. We're gonna, just as before, we're gonna use some improved algorithm for a fixed matrix like the 8x8 Hadamard transform and use it recursively somehow to get an improved matrix for Hn for all n bigger than 8. Okay, but the same kind of thing we just talked about. So here, more specifically, the fast Walsh-Hadamard transform, it computes H8 using 24 operations, like 8 times log base 2 of 8 is 24. And I'm going to show you how to improve it from 24 to 23 operations for the 8x8 Walsh-Hadamard transform. And that's where our improvement is going to come from. And I'm actually not exactly going to do that. You'll see we're going to compute something very similar to the Walsh-Hadamard transform using 23 operations and then do some tricks to use it to actually compute the Walsh-Hadamard transform. So that's the idea. We're going to like improve from 24 to 23. So it'll give a leading constant of 23 over 24, which is a bit less than 0.96. So that's the whole idea, that we're going to get an improved algorithm for some fixed matrix again. So once again, we're going to start with that same like rigidity upper bound for H8 that I just showed you. So here is H8. And I'll write it just like before as the sum of a sparse matrix plus a low rank matrix. Technically, this is slightly different. I'm putting a 1 here instead of a minus. So now it's a rank 2 matrix, the matrix with 1 fewer non-zero entry in it, but it's more or less the same thing. So this is our starting point. How are we going to use this to get a better algorithm for H8? So our goal is to, given as input a vector of 8 numbers, I'll call it A, B, C, D, E, F, G, H. We want to multiply H8 times that vector. So I want to multiply the sparse matrix times that vector and the low rank matrix times that vector and add them together. And sort of the intuition is that this is a good idea because sparse matrices and low rank matrices can both be multiplied times a vector using few operations. So we're going to take advantage of that and then combine them together. So let's work out the details. Okay. Well, in the sparse matrix, we can see that the first row is all zeros, and every row after that has 3 2s in it. So each of those 7 on 0 rows needs 2 additions and 1 multiplied by 2 to compute the vector times that row. So for example, in that second row, you can see it's supposed to be computing 2 times C plus 2 times E plus 2 times G. You can compute that by doing 3 operations, 2 additions and a multiply. Okay, so in total, doing the first matrix times a vector, you can do with 21 operations. The second matrix, we're going to take advantage of the fact that it's low rank. So we'll first compute just the sum of B plus C plus D all the way up to G, like the rows 2 through 8 of the matrix. And then the first row is A plus that, and all the other rows are A minus that. Okay, so the second matrix we can do again with a total of just 8 operations. So these are 2 matrices we can compute with very few operations. And then we also have to combine them together at the end to compute H8. So we have these results, and we have to add, for each row, we have to add the 2 results together. For the top row, we don't need to do anything because we already had like all zeros for the first part. So we're just adding 0 to something. But for each of the other 7 rows, we have to add the result of the first matrix plus the result of the second matrix. So we get 7 more additions. So in total, we get 21 plus 8 plus 7, which is 36 operations to compute H8 times a vector. And this is way more than 24, which is what we're trying to beat. Okay, so this is our starting point. Like maybe it's intuitively a good idea, but you work out the details and it doesn't work so well. But I'm nonetheless going to take this algorithm and like apply a bunch of tricks to it to get down to 23. Okay, so let me show you the tricks. And the details, if you don't follow the details, is not super important. I mostly just want to show you like the structure of what kinds of things we're doing. So to start, let me rewrite what I said here. Like, let me actually write down the equations we're doing. Okay, so here it is. So we first compute this total, which is B plus G up to H, and the difference, which is A minus that. And then we can see row 1 is supposed to be A plus the total, and rows 2 through 8 are each this difference plus 2 times some sum of 3 numbers. This is the same thing I showed you before. This is like more concretely the algorithm I just described to you. And you can count and see that this is 36 operations that I've written here. Okay, so let me transform it a little bit. The first thing I'm going to do is just some rewriting. So I'm going to like move the multiplications by 2 from the end of the algorithm to the beginning. This isn't going to change the operation count, but it's going to be useful later on. So what I'm going to do is at the very beginning, compute for each of B through H, like I'll compute B prime is 2 times B and C prime is 2 times C and so on. So I'm, instead of doing 7 different multiplies by 2 at the end, I'm going to do 7 different multiplies by 2 at the beginning. And then over here, like for example, instead of doing 2 times C plus E plus G, I can just do C prime plus E prime plus G prime, and so on. So I can do that replacement. So I just subtracted 7 multiplies from 2 at the end and added 7 multiplies by 2 at the beginning. Okay, that's the first, just a rearrangement. So we haven't changed the operation count so far. Okay, now I'm actually going to do a trick to change the operation count. The trick is I'm going to notice that there are some additions. I'm going to take some of the additions that we're doing over here and do them a bit earlier so that I can reuse them. Okay, so more concretely, I'm just going to move this down a bit. So before doing this, I'm going to compute B prime plus C prime and D prime plus H prime and F prime plus G prime. So I'm doing these 3 additions. It's okay to do these over here because I was also going to do those over there anyway. Like B prime plus C prime, I was going to compute over here anyway. So I can, instead of doing it there, just replace it with T1 and T2 and T3 that I've computed earlier. Okay, so once again, I just moved 3 additions from later to earlier. So I haven't changed the operation count at all. But the reason I'm doing this is now I can use T1, T2, and T3 to save on the operations for computing total over here. So right now I'm computing total using 6 operations, but instead I can add T1, T2, and T3 and E prime, the one that's missing, and divide by 2. And now I'm computing it with only 4 operations instead. Okay, so that's trick one. I'm just reusing some of those additions in the rows to also compute total a little bit faster. So I've decreased 2 operations so far. Yeah, this is the kind of thing we're going to be doing. Okay, let me do one more trick like this, which is to notice that over here we can also save a few operations. So as an example, if you can look in row 2 and row 3, both of them we could start by doing diff plus e prime. So like here we can do diff plus e prime, here we can do diff plus e prime. I think there's a third one here where we can do diff plus e prime. So we're just going to do that once and then use it all 3 times instead of doing it 3 times. So I'm ahead of time going to compute diff plus d prime, diff plus e prime, and diff plus h prime. And then over there on the right, I'll use those instead of adding diff plus things in the first place. So here I did 3 new additions, but over there I saved 7 additions. So I actually decreased the operation count by 4. Okay, so we started with 36 operations. So far we've saved 6 operations doing these tricks. Now we're at 30 operations, which is still worse than 24 operations. Okay, but actually, okay, this is the end of the little tricks like this. I'm going to stop now and just make some observations about what we have. So our current count, like I just said, is 30 operations. But one observation is that actually 7 of our operations are just these multiplied by 2s at the very beginning, which are somehow very simple operations compared to the rest of what's going on. So if it were somehow possible to get rid of those multiplied by 2s at the very beginning, then we'd be down to 23 operations, which is like what I told you our goal is. Okay, so one observation we can make about the algorithm is that actually after computing these b prime through h prime, the whole rest of the algorithm now actually only uses b prime through h prime. It doesn't use b through h anymore. Like once we have these times 2s, we don't care about the original not multiplied by 2 values anymore. So in particular, what I have here, you can equivalently see it as an algorithm that uses only 23 operations, like ignoring this, which given as input a and 2b and 2c and 2d and so on up to 2h outputs the Hadamard transform of a, b, c, d up to h. Okay, so I gave you, this is actually an algorithm with 23 operations for something that's very similar to the Hadamard transform, except it assumes we're given as input some of the entries multiplied by 2 instead of not multiplied by 2. Okay, so it turns out this will be totally fine, and we're going to be able to use this to make a Hadamard transform algorithm. And this, if you've seen these like fast Fourier, like modified split radix fast Fourier transform algorithms, they do a very similar kind of trick to also to speed those up. So to get into that, we have to ask the question, how do we actually convert an algorithm for H8 into an algorithm for Hn for all n? And to answer that, I'm going to start with an even simpler question. How would we convert an algorithm for H2 into an algorithm for Hn for all n? So we know at the near the very beginning of the talk, we did this. We gave this algorithm called the fast Walsh-Hadamard transform, where you do 2 recursive multiplications by Hn over 2, and then you add and subtract them at the end to get our final answer. So let me just rewrite that like in more of an algorithm-y way. So to compute Hn on input v, you first let a be the Hadamard transform of the first half of the vector, and you let b be the Hadamard transform of the second half of the vector, and then you let the first half of the outputs be a plus b, and the second half of the outputs be a minus b, and you return that. That was our fast Walsh-Hadamard transform. I want to rewrite it again in a slightly more suggestive way. So to compute Hn on input v, I'll still compute those 2 recursive calls. And then for this combining at the end, what you can see is it's equivalent to, for each I between 0 and n over 2 minus 1, the ith and n over 2 plus ith output entries are actually the 2 by 2 Walsh-Hadamard transform times the vector of the ith entry of a and ith entry of b. Like here we're doing a plus b and a minus b, which is exactly the 2 by 2 Hadamard transform, and then outputting y at the end. So it turned out when you like write out why this happened, you can do the exact same thing for the 8 by 8 Hadamard transform or any size. So you get an analogous algorithm where on input v, you first split it into 8 parts and you recursively compute the Hadamard transforms of all those 8 parts and so on. And then for each I between 0 and n over 8, these like 8 entries of the output are the 8 by 8 Hadamard transform times those 8 entries that we got from our recursive calls. And then you return y. So that's how we could recursively use H8 to compute Hn for all n. But we don't have a fast algorithm for actually doing H8 times this. We only have a fast algorithm if instead of being given A, B, C up to H, we are actually given A and B prime, C prime all the way up to H prime, which are 2 times Hn over 8. So this, okay, so now we have to ask ourselves, is this a problem? So if we had, if we had an algorithm for computing Hn, and we also had an algorithm for computing 2 times Hn, this would be great because we could use one of them for the first call and the other for the other recursive calls and so on. But then in our algorithm for computing 2 times Hn, we would need an algorithm for computing 2 times Hn and an algorithm for computing 4 times Hn and so on. So what we're going to do is just for any k, we're going to make an algorithm for computing 2 to the k times Hn. And it's going to work exactly like this. It'll make one recursive call to 2 to the k times Hn and 7 recursive calls to 2 to the k plus 1 times Hn. And then it can combine them together over here. Maybe this is supposed to say 2 to the k using the 23 operation algorithm that I showed you before. And the trick is, you can see now at every recursive step, we're like kind of ignoring the fact that there were these extra multiplies by 2 and pushing them down to the next layer of recursion and pushing them down to the next layer and so on. And we only care about them all the way at the bottom at the base case. So at the base case, we have to multiply our input by some big power of 2, which conveniently we can do with a single arithmetic operation. And then we like push them all up the recursion and get the answer that we're hoping for. So we get the recursion that, if T of n is the number of operations to compute 2 to the k times Hn for any k, like you can think of it as the max overall k or something like this. Well, T of 1 is 1, so you have to compute 2 to the k times your input, which you can do with one operation. And then we get our nice recursion using the thing that I've hidden behind this blue box, which is that to do on a size n, you do n over 8 calls for a size n over 8 plus 23 over 24 times n over 8 operations to do this algorithm over here. And you solve this and you get 23 over 24 times n log n operations for the whole thing. Yeah. I think that's it. Thanks. Yeah. Yeah, I thought here at the theory lunch, nobody would ask me something like that. Yeah, more honestly, I'm really not the best person to ask. I think it should. I mean, like our algorithm is not too complicated. And in fact, a lot of the operations really are multiplying and dividing by powers of 2, which like when you really implement them, you can do with bit shifts that are typically quite a bit faster than other operations. But on the other hand, like people have developed really optimized Hadamard algorithms in real life that like really heavily take advantage of cache hits or distributed systems and so on. So it would, I think, at least take quite a bit of engineering work to make it practical. But my hope is that the answer to your question is yes. Yeah, it's like, I don't think we're doing anything super, super complicated. So I don't see why not, but it would at least take some work. Yeah. Yeah, it's sort of like in the previous FFT algorithms, there's some nice like code you can write that does the basically the previous ones were uniform algorithms, if you know what that means, and this new one is a like very non-uniform algorithm that has to do some complicated things to even figure out what complex numbers it's multiplying it by at every step. I at least chatted with the author Igor for a while, and like he told me like he doesn't think there's any hope of like even implementing what his algorithm is for it. Yeah, I mean I hope so. I've been thinking about it recently. Yeah, as you might know, there's been like quite a bit of work on trying to prove rigidity lower bounds for these matrices. So we know sort of something from the lower bound and something from the upper bound. I think we know it's at least like 1 plus epsilon times log n or something like this. Like basically not really. We don't know very much about it.
It would be very difficult region, but it turns out that there within that region would be another.
Yeah.
proof that,
Yeah, maybe there's another proof that it's even less rigid than we think it is. Exactly. Yeah. Just to be.
There is no reason to do this. How hard have you tried?
I've tried a little bit, not too much.
But that's not that. You're very good at doing it. A random matrix is very non-rigid.
Yeah, I think we have like only very weak techniques for proving lower bounds on rigidity, and only like one technique, which I sort of just mentioned, for proving maybe 2 techniques for proving upper bounds. We don't. I think it's still a big open question. Yeah, actually, another neat question is, so like here we sort of used the non-rigidity of the Hadamard transform to make a faster algorithm for the discrete Fourier transform. But there's a nice paper by Ziv and Al and Lu where they showed that actually the discrete Fourier transform itself is not rigid. So I think it would be exciting to like more directly use that to get a faster algorithm. But I at least tried a little bit and couldn't figure out how to do it.